In this video, we'll explore a similar example as the previous one. Here we have a force being applied to a particle, and that force has a magnitude defined by cos of pi x over 3. Our question is how much work, energy, is consumed, or how much work is done by moving the particle not from the origin, but from x equals 1 to x equals 2. So just to frame our argument again here, we have x equals 0, but we're going to start moving at x equals 1 and then go to x equals 2. The force required to move the object is given by cos of pi x over 3. And then the natural thing to ask is, can we simply use work equals force times distance? And the answer is no, because the force is changing or variable, or not constant. Any one of those reasons. Between the point x equals 1 and x equals 2, we're going to have different x values, and that's going to result in different forces. So which force would we use in this calculation? There's no single force, so we need another strategy. Fortunately, the strategy we have developed already works like a charm here. Imagine moving this particle a little bit, a little bit, and a little bit. How much are each of those little bits? Delta x sounds like a convenient notation to use, or a convenient interval to use. And so the work to move from some position x to some new position, x plus a little bit, x plus delta x, is going to equal work, which is force times distance, which is going to be our cosine pi x over 3 times the distance we're moving, which is delta x. And the reason we can use that is because this is approximately constant on that small interval. That is our gateway. We can't go the entire span all at once because the force would change noticeably over that interval. But on a tiny little interval, especially one that we're going to let go to 0 later on, we can treat that force as constant over that tiny interval. And that leads us very quickly to our total work calculation, which is the sum of the work for all intervals. And we represent that with our integral. And the only difference is, or the only change we have to introduce, is that our delta x has to become a dx, and otherwise everything else stays exactly the same. Now that's not quite done yet. Both from a mathematical perspective, we need a final value for this, not an indefinite integral. And also there's a piece of the question that we haven't used yet, the x equals 1 to x equals 2. Both of those point towards needing limits of integration in our question. But that defines perfectly an integral that computes the total work done as we move by little delta x increments from x equals 1 to x equals 2. Now all that remains is do the calculation. So our work is that integral from 1 to 2, cos of pi x over 3 dx. And again, now we can just think of this as a general antiderivative problem. And what we need to differentiate to get cos, we need sine of the same function. The only challenge is this multiplier here, this pi over 3. We would divide through by that. This is our guessing and checking. So that if we took a derivative with respect to x here, a pi over 3 would come out, they'd cancel, and we would get back to exactly our cosine function with no extra constants running around. And then we would evaluate that between x equals 1 and x equals 2. Let's tidy that up. We'll flip the fraction around, and then we'll do our sine of pi times upper value, 2, minus the sine of our lower value, which is 1, over 3, and there we go. Sine of 2 pi over 3. You can use triangles or your calculator. It'll be the root 3 over 2, or 0.866. And sine of pi over 3, calculator triangles. Oh. Also 0.866. So that equals 0. Okay, that seems a little surprising. I think we need some explanation for that. Let's recast what we just did here, focusing on the region that we were in. This is our x values, 1 to 2. And just for a moment, let's talk about graphing our force value here. Most of our intuition around work is that we're pulling in a direction corresponding to delta x, so the force and the distance are in the same direction, so we get a positive contribution all the time. However, if you think about the graph of cos pi x over 3, and think about, let's say it's period, the period is going to be 2 pi divided by that pi over 3. And so that period is going to be, cancel, cancel, we're going to get 6. And so that means interesting things are going to happen at, let's continue this line a little bit further, get to 3 here. At 3. And we're going to have that be a half cycle. So cosine graph starts at a peak. At the end of half a cycle, it gets to the bottom. Halfway in between, it hits 0. That is going to be our graph of the force applied. And there we see what's happening. As we're pulling to the right here, we have a positive force times the distance. And then over here, what's happening is we're actually pulling back the other way, if you like. The force is acting in the other direction while still pulling in positive delta x directions. As we pull in this direction, we're having to exert force to move it. But as we get to this region here, it's like there's something pulling us back. We're actually gaining energy back. And the net effect, because the force is perfectly symmetrical over this interval from 1 to 2, is that we get a perfect cancellation, like we see in the result, and get a net energy change of 0 through this thing. Now, this might be a challenging force to find in nature, but from a mathematical perspective, it works out perfectly that we should get a 0 value for the work computed here because of this change in the sign, or this change in direction of the force.